activity coefficient. Activity coefficient is a measure of how much a solution differs from an ideal solution. Activity coefficient of individual ions can never be determined, because in a strong electrolytic solution, cations are always accompanied by anions and vice versa. Therefore, gamma plus, which is activity coefficient for positive ions, and gamma minus, which is activity coefficient for negative ions, cannot be determined individually. Thus, a new term is defined as mean activity coefficient. The symbol is gamma plus minus. Mean activity coefficient is a measure of ion-ion interactions in solution. The equation is this, where mu plus is the number of cations with positive charge and mu minus is the number of anions with negative charge, while mu is the sum of mu plus and mu minus.
So for NaCl, for example NaCl dissociate into Na plus and Cl minus. So untuk cari mean ionic activity coefficient for NaCl, kita boleh tulis gamma plus minus NaCl is equal to gamma for positive ion is Na, and the nu plus is 1, and gamma for activity coefficient negative ion is Cl minus, and the nu minus is 1, so 1 over nu is 2. So untuk cari mean activity coefficient to NaCl, kita boleh tulis macam ni. And untuk Na2CO3, dia akan dissociate into 2 Na plus and CO3 to minus. So kita boleh tulis mean ionic coefficient for Na2CO3 is gamma plus minus Na2CO3 is equal to gamma plus, which is activity coefficient for positive ion, which is Na plus. So nu plus is 2, and gamma minus is activity coefficient for negative ion, which is CO3 to minus, and the nu minus is 1, so we don't write it, so the nu is 3. Contoh kita ada nilai untuk gamma Na plus and gamma CO3 to minus. Contoh, it is impossible untuk kita dapat sebab kita tak boleh nak determine activity coefficient untuk ionic solution separately, positive and negative charge ion. So contohlah kita dapat gamma Na plus, kita dapat 0.78, and gamma CO3 to minus kita dapat 0.52. So untuk cari mean ionic activity coefficient for Na2CO3, kita just masukkan je dalam equation yang ni. So kita akan dapat plus minus Na2CO3 is equal to 0.78 kuasa 2, sebab dia punya nu plus is 2, and didarabkan dengan 0.52, and kuasa 1 je sebab nu minus dia 1, and kurungkan power of 1 over 3. So kita akan dapat nilai dia 0.68. Ini contoh kalau kita ada nilai untuk setiap activity coefficient untuk positive and negative ion, tapi it is impossible. So untuk experimentally, we can see explanation from Debye-Hackl. Kita boleh tengok kat situ for experimentally punya.
The Debye-Hackl theory is based on 3 assumptions of how ions act in solution, which is the first one is electrolytes completely dissociate into ions in solution. Solution of electrolyte are very dilute, on the order of 0.01 m. Each ion is surrounded by ion of the opposite charge on average. The second is about the Debye-Hackl. A theory to explain the non-ideal behavior of electrolytes published in 1920 by Peter Debye and Erich Hackl. It assumes that electrolytes in solution are fully dissociated and the non-ideal behavior arises because of electrostatic interaction between ions. The theory shows how to calculate the extra free energy per ion resulting from each interaction and consequently the activity coefficient. It gives a good description of non-ideal electrolyte behavior for very dilute solution, but it cannot be used for more concentrated electrolytes. The next one is about the equation of Debye-Hückel-Lewontin law. Debye and Hückel developed the following equation to calculate the mean ionic activity coefficient. The equation is about the Debye-Hückel-Lewontin law. The ionic strength is calculated by the following relation. Since most of electrolyte solution we study are used in the form of aqueous and have a temperature of 298 Kelvin, the Lewontin law of equation on the side reduced to, as you can see at the bottom of the picture.
Okay, basically this is the example questions where the question asks us to calculate the mean activity coefficient for a 0.02 mole aqueous solution of calcium chloride. So in order to solve these questions, we need to use this formula, which is this formula came from the Debye-Hückel-Lewontin law equations. Okay, in this formula it contains A, which is A is a constant value in aqueous with a value of negative 0.509. I here is the ionic strength where we need to use this formula in order to get the value of I, and Z plus Z minus is the charge anion and cation. So basically, in order to solve these questions, we know that as the calcium chloride dissolves, it will form 1 mole of calcium ion and 2 mole of chloride ion. So firstly, we are going to find the value of I, which is the ionic strength, by using this formula. Okay, as we get from here, 1/2 times 0.02. 0.02 here is the molality given in the equation, plus 2 here is the charge of calcium ion, plus 0.04. 0.04 here is because 0.02 times 2 because 2 mole of chloride ion is formed, times 0.02, that is the molality given in the equation, and -1 here is the charge of chloride ion. So as we get the calculation, we know the answer is 0.06. So we are going to use this value and other value given to insert in this equation in order to get the mean activity coefficient. So basically the value of A is 0.509, and the charge of calcium ion is +2, the charge of chloride ion is -1, and 0.06 here is the I value, and don't forget the square root. So we got the value is -0.25, but this is for the log mean activity coefficient. We only want the mean activity coefficient only, which is the lambda. So we got to anti-log this answer. So we got the final answer 0.1627. Okay.
Extended Debye-Hückel law. Why it is extended? It is because when the ionic strength of a solution is too high for the Debye-Hückel-Lewontin law to be valid, as example, the molality of the solution is too high, so the mean activity coefficient may be calculated or estimated from the extended Debye-Hückel law equation below. Based on the equation, A is equal to 0.5085, B is equal to 0.3281. Both A and B are constant at 25 degrees Celsius in water. Meanwhile, AI is equal to size or effective diameter of the ion in angstrom. This extended Debye-Hückel law equation provides accurate result for ionic strength less than 10 to the power of -1. Values of gamma I for different ions can be calculated using this formula, and the values of AI can be shown in this table.
What is the activity coefficient for K+ in 0.05 molar KCl? To solve the equation, we have to identify the dissociation of the solution, the extended Debye-Hückel equation, ionic strength, charge of the ions, and effective diameter of the ion, which is K+. Okay, first, calculate the ionic strength. The formula is half times with the sum of the concentration times the square of the charge of the ions. Therefore, we can write the equation as half times the concentration of potassium ion times charge plus 1 square plus the concentration of chlorine ion times negative 1 square. Since we have 0.05 molar of solution, we also have 0.05 molar of potassium ion and 0.05 molar of chlorine ion. Substitute the concentration value into the formula and we will get the ionic strength of the solution equals to 0.05 molar. Second thing that is needed in the Bai-Hakel equation is the charge of species K+, which is plus 1. Number 3, we have to know the ionic size of the potassium ion from the table, which is 300 picometer, but we have to change it into nanometer, which give value 0.3. So now we have all the information needed. Therefore, we can use the Debye-Hakel equation. Negative log gamma K plus equals to A times charge square times square root of ionic strength. Divide by 1 plus B times alpha square root ionic strength. Substitute the value and we get the value of gamma K plus equals to 0.865 or 0.81.